Hi, welcome back. Okay, so on this video we are going to revise on the topic of forces, or rather it's called dynamics, okay, as to how object moves and how to calculate such movements. Okay, so let's go into it. Now the first thing that you all learn in dynamics are Newton's law. Okay, so we have Newton's first law and Newton's second law. Alright, Newton's second law is the famous mass times acceleration. Yes, it's mass. So mass times acceleration equals to this thing called the net force or the resultant force. Okay, yeah, so based on the spelling, right, I think everyone would prefer writing net force more than resultant. Okay, but anyway, mass and acceleration equal net force, and Newton's first law states that when object in motion, when object at rest, it will continue at rest. When in motion, it will continue in motion as long as no net force, no external force acts on it. Okay. Okay, so in other words, right, it's either the speed is at zero or the speed is at constant. Okay, and when this happens, right, this means that the net force acting on it is zero because nothing will act on it. Okay, if net force is more than zero, that means something is acting on it. Okay, so when at rest, it will continue at rest. Okay, that means that the speed is zero. When in motion, the object will continue in motion. That means that the speed is constant. Okay, and take note that the net force here is 0 Newton. Okay, the second one is F equals to ma. Okay, so before we look into Newton's law in more detail, we need to identify the idea of net force. Okay, so let's say I have a box here. Okay, someone pulls it by 5 Newton to the right, someone pulls it to the left by 4 Newton. We know that the F net here is 1 Newton to the right. Hey, this is what I mean by net force, just a resultant force. Okay, that means the resulting force here. Okay, let's say I have another box, right, that is being put up by a string 5 Newton, put down by a string by 3 Newton. The weight is 3 Newton. Okay, this thing will go up. Okay, and that's how an elevator works, right? For the elevator to go up, the tension in the string must be higher than the weight of the entire lift. Okay, so F net is 2 Newton upwards. Okay, so F net is not just confined to left or right. Okay, it's also confined to up. It's also given to up and down and a lot of other directions. Okay, so let's say I have a ball here and someone pulls it here by 4 Newton here, and someone pulls it by 2 Newton here. Then we have F net equals to 2 Newton in this direction. Of course, when you deal with this direction, usually it's not in your syllabus unless you are drawing vector diagram. Okay. Okay. Yeah. Okay. So that's the idea of F net. Now, so we know that F net goes in the direction of superior force. Okay, so whichever force is bigger, it will go in that direction. Okay, we know that F net is calculated by subtracting opposite directions, right? So if I'm left and you're right, then we subtract each other. If you are right and I'm right, then we will add to each other. Okay, so let's say I have 3 Newton here, 4 Newton here, and 7 Newton here. Okay, so this, in this case, it will be 7 minus 3 plus 4, which is 0 Newton. Okay, so this object will remain at rest. Okay, based on Newton's first law, it will remain at rest. Okay, it will not move. The F net is 0, so in this case F net equals 0 Newton. Okay, so take note of, first thing, how I have summed these two up because they're in the same direction, how I took this minus this because they're in the opposite direction. Okay, so maybe I should circle it in red. Okay, so I take this minus this, right, because they're in red now, opposite direction. Okay, so that's the idea of net force. Okay, I hope it helps. Now we now look at Newton's first law again. Okay, so Newton's first law states that When object at rest, it will continue at rest, so we have 0 meter per second. When it's in motion, it will continue motion, so that's constant speed. And all these links up to net force being 0 Newton. Okay, and net force is 0 Newton is one of the conditions for equilibrium. The other condition is that the net moment must be 0. Okay, so that it does not rotate. Okay, because I can have an object that's like this. Okay, I put a force here, let's say 5 Newton. I put a force here, let's say 5 Newton. Now, yes, upward minus downward is equal force. Okay, so nothing happened, but it will start to rotate. Okay, so net force being 0 Newton is one condition. Net moment being 0 Newton meter is the second condition for anything to be in equilibrium. Okay, now we look at Newton's second law now, and after this, we'll do some example. Okay, so Newton's second law states that F net equals to ma. So basically your F equals to ma, yeah. Now this is mass, it's always in kg. Okay, this is acceleration, this is always in meter per second square. Alright, so obviously F net is in newtons. Now the question can come in a few form. Maybe you need to find F net in this manner. Okay, so maybe after you find F net, okay, then they give you the acceleration and you're supposed to find the mass. Okay, so it really depends how the question wants to vary. Okay, but for simplicity's sake, okay, let's say I have a box. It's moving at 3 meter per second square, and this is 2 kg. Okay, very simply, we know that F net equals to 6 newtons. Now, if let's say we make the question slightly more complicated, this is 2 kg, and there's friction acting on it. Okay, and they tell you that the acceleration is 2 meter per second square now. Okay, so previously there's no friction, right? But now there's friction. Okay, so they tell you that the acceleration has decreased. Then they ask you to find the friction. Okay, so previously when the acceleration wasn't in play, right? It seems like there's a 6 Newton force here. But now with the friction in play, it seems like there's a 6 Newton force here, but there's friction, and they want to find the friction. Okay, so first let's find the F equals to ma part, because it seems like the F net has dropped, right? So F net equals to ma, which is in this case 2 times 2, which is in this case 4 Newton. Okay, so previously it was being pulled by 6 Newton, but now the F net is only 4 Newton. In other words, right, we only can conclude that F net, right, is also equals to 6 minus friction, which will give us 4 Newton, and therefore that will leave us with friction equals to 2 Newton. Okay, you get it? Okay, so this 6 Newton, when there's no friction, the box experiences the F net of 6 Newton. That is only possible, right, if someone is pulling it with 6 Newton to the right. However, when it comes to the ground where there's friction, right, it slows down. If it slows down, the person pulling it to the right is still pulling at 6 Newton. We can conclude that the friction is, in this case, in this very specific case, is 2 Newton, since F equals to ma gives us 4. Alright. Okay, so that's the idea of Newton's law at work. Okay. So I think this is quite a typical question in your O level. Okay. Apart from F equal ma, right, I want to talk about this thing. Okay, so let's say I have 2 boxes. Okay, they are connected by a string. Okay, by the way, in your physics, right, there are 3 main forces that you must take note of. Okay, so weight being one, tension, okay, that will only appear in strings and whatnot, strings, ropes, anything that ties you up. Okay, so they will appear there. Tension. Okay, so let's say I have a box hanging by the ceiling, right? Tension is upwards, weight is downwards. That's why it can be hung there without falling down. Okay, so tension always acts towards the support. Alright, so then now of course you have your friction. Okay, or your air resistance, whichever medium you are in. Okay, if you are on the ground, then obviously it's friction. If you are in the air, then obviously it's air resistance. Okay, I think, yeah. Okay, so over here we have two boxes. Okay, they are tied by a string. Okay, so let's draw it nicely, sorry, without so many lines. Alright, so let's have a box here, then it's connected by a string. Let's draw the string in red. Okay, and then let's draw this again. Okay, so something like this, right? Now if let's say the box is moving, right? Okay, so someone is pulling it with say 10 newtons here. Okay, now the question is then going to be asked that I want you all to identify is that if let's say this is 3 kg and let's say this is 2 kg. Okay, let's say the net force of this system. Okay, so there are a few ways to look at it. You can look at it as though like this is a 5 kg block and it's being pulled by the 10 newton force. Okay, let's say there's no friction to not complicate matters, right? Okay, seriously, it's just like this. Alright, so F net equals to 10, so equals to MA equals to 5A, so A equals to 2 meter per second squared. Now in other words, this thing is 2 meter per second squared. Alright, what I want you to note is that for these two boxes, right, they have to have the same acceleration. Why? Because if they don't have the same acceleration, right, then the string will snap. It's either they will end up colliding with one another. Okay, so this thing goes faster or this thing goes slower. So either way, this string will snap. Okay, which will not be the case. Okay, so in that sense, both will move in the same rate. Okay, then the string will snap. Alright, so if you work it out, right, F equals to MA. Okay, so you work it F equal MA here, you get 4 Newton. You work it F equal MA here, you get 6 Newton, and it actually adds up to 10 Newton, right? Okay, showing that this theory, this concept is correct. Okay, so that's just something I want to go through additionally. Okay, if you can understand this example, apply the principle to this example, you should be able to do forces from now on. Alright, so I'll start the video here. I hope this helps.